So now we're going to continue on with our lecture 2, and we're going to discuss in this video the graphs of the remaining 4 trigonometric functions, namely the tangent, cotangent, cosecant, and secant functions. So periodic properties, the tangent and cotangent functions both have periods of pi, whereas the other 4 trigonometric functions have periods of 2 pi. So that means you calculate an output of the tangent function, for instance, at a terminal number of x, and that output will reappear for if you were to add pi to terminal number x. And we'll see that when we graph the tangent function over several periods. So recall the definition of the tangent function. It is a ratio of the sine function to the cosine function. Okay, so it's an odd function. So the tangent of a terminal number is equal to sine of x divided by cosine x. So it's a rational function, right? And so that means that the tangent function is not defined where cosine x is 0. Likewise, the cotangent function is the reciprocal of the tan function. So cotangent of x is equal to cosine x divided by sine x. And the table right here on the right is a function table for the tangent function over 1 period. So let's see, where's that 1 period? Over a half period, I would say. Okay, so from 0 to pi halves. This is the approximate. This last row, x is 1.5707 is the approximation for pi halves. So that's a half of a period of the tangent function. And we can see that as we get closer and closer to pi halves, we know that the cosine of pi halves is 0. So we can't plug pi halves directly into the tangent function. We can only get closer and closer to pi halves and analyze the output. So as we get close to pi halves, of course, looking here, the sine function will get closer and closer to 1 in the output because it's a continuous function. And the cosine function the output of the cosine function gets smaller and smaller. So if we have a number divided by a very small number, then the output, of course, goes larger and larger, as shown in this table. And the tangent of 0 is 0 because the sine of 0 is 0 and the cosine of 0 is 1. So that makes the vertical asymptotes. So if you recall from the first lecture of the class, the vertical asymptotes will occur where the denominator is equal to 0. And we know the cosine function is 0 at x equals pi halves. And since the cosine function is an even function, okay, the cosine of pi halves, because it's an even function, we know that the cosine of a number must equal to the cosine of the negative of the number. Okay, so if the cosine of pi halves is 0, then the cosine of negative pi halves is 0. And so these would constitute vertical asymptotes for the tangent function as shown in this figure right here. And then we just go ahead and we use the function table to plot the remaining values. So basically it's not that hard to calculate. So for instance, we can calculate the tangent of pi 6 just knowing what we know about sine and cosine of pi 6. So the sine of pi 6, the tangent of pi 6 is the sine of pi 6 divided by the cosine of pi 6. All right, so and we can recall what the sine of pi 6 is because we proved this in one of the earlier chapter 2 lectures. And I asked you to memorize this, okay? or you can look it up in the table, which is portrayed in a previous lecture. So the sine of pi 6 is 1/2, and the cosine of pi 6 is the square root of 3/2. So that makes the tangent of pi 6 equal to 1 over the square root of 3, which is equal to the square root of 3/3, which is equal to 0.58. Okay, and you can see, you can complete the rest of the table actually without having to use a calculator, at least if x is one of the standard reference numbers or standard terminal numbers that we're accustomed to, say pi 6, pi 4, pi thirds. The decimals, of course, you'll need a calculator for. Okay. All right, so the red graph for the tangent, of course, originates from the function table, and then we do the same thing for the cotangent function. Basically, we generate the graph from a function table. Or we can deduce values of the cotangent function from its definition. So the cotangent function, of course, will have vertical asymptotes where the sine function is equal to 0, and the sine function is equal to 0 at x equals 0 and at x equals pi. So these two graphs depict the tangent function and the cotangent function on one period. So they're not labeled, are they? So this is tangent of x, and this is the cotangent of x. Note carefully the x-intercepts. Okay, so the tangent function has an x-intercept at x equals 0. The cotangent function has an x-intercept at pi halves. Now, these functions are periodic, as you can see with pi, so we'll discuss shortly how we could graph these functions over several periods. Yeah, so one period of tan x, one period of cotangent x. All right, so let's see, we can talk about the other two, cosecant and secant function, and they're real easy to graph as well. Probably the easier, just requires a little bit of work, but let me paste the picture in for the cosecant and secant functions. All right, so the first graph is one period of the cosecant function, and you may recall the definition of the cosecant function is equal to 1 over sine x, the reciprocal of the sine function. So that means where sine x is equal to 0 would make for a vertical asymptote for the cosecant function. So the blue curve right here, shown right here, is sine x. And so you see where the 0 crossings for sine x would happen at 0, pi, and 2 pi. So those would have to translate into vertical asymptotes as you take the reciprocal of the sine function. And of course, the sine function is 1 at pi halves, but the reciprocal of 1 is 1. So 1, 1 would be a point on the cosecant function. And the sine function at 3 pi over 2 radians is -1, and so the reciprocal of -1 is -1 as well. So essentially, this gives you the mode or the method for graphing the cosecant function. To graph the cosecant function, sketch the graph of the sine function, identify the vertical asymptotes, identify the local min and the local max. This is a local min. This is a local max. Okay, even though the local min is above the local max, identify those points, and then from there draw the corresponding branches that will be asymptotic with its asymptotes. So why is this a local max right here? Well, by definition, a local max is a transition from an increasing part of the function to a decreasing part. So when you transition from increasing to decreasing, you have a local max. This point is a local min because you're transitioning from decreasing to increasing. Okay, so that's how you deal with the cosecant function. Its period again is 2 pi, and we'll graph periodic extensions of this shortly. All right, now the secant function, as you know, is 1 over cosine x. So secant of x is equal to 1 over cosine x. And so wherever cosine x is equal to 0, that would translate into a vertical asymptote for the secant function. So again, the blue curve is one period sketch of a cosine function. The cosine function is 0 at pi halves and at 3 pi over 2, so those would constitute vertical asymptotes for the secant function. And likewise, at x equals 0, the cosine function is 1, and the reciprocal of 1 is 1, so the secant function has an output of 1 at x equals 0. Okay. So you have a local min right here. You have a local min at 2 pi and 1, and then you have a local max at pi negative 1. So those are the graphs of one periods of the secant, cosecant functions. All right, and so now let's talk about the periodic extension of the tangent and cotangent functions, as well as the secant and cosecant functions. So they'll look something like this. Let me grab a picture, paste it into whiteboard. So pull up my all right, and so here's the periodic extension of the tangent function. So we know that the tangent function has a period of pi as well as the cotangent function. All right, so we've already seen the structure of the first branch, which I'll accentuate in, say, blue. Okay, the first branch, we have an x-intercept and it's periodic, and it's asymptotic, that is, with negative pi halves and pi halves. It's an odd function, so you know by an odd function, if this is a point on the tangent branch, then the negative x, negative y will be its symmetric counterpart. Negative x, negative y, okay, by the odd property. So to graph the periodic structure of the tangent function, you just take this blue branch, copy it, and then paste it on the next period. Okay, so the first period is you start right here. You consider negative pi to, and we'll discuss this in the future when we talk about principal parts of the function. But consider this branch that I've accentuated here as the principal period of the tangent function from negative pi halves to pi halves. And of course, the reason why I selected here is because the tangent function flows through its complete range of output values. In other words, it ranges from negative infinity to positive infinity on this interval. And so that's basically our notion of a period. One period of the function is defined where the outputs of the function transition through its full range of values. All right, so with that in mind, you take this blue piece and you copy it, and then you start at pi halves, and then you paste it. Okay, and so by periodicity, each point on the next branch will be the point on this branch, on the blue branch, shifted to the right by pi. Okay, so you just paste it at the end of pi halves, and you keep pasting. All right, and then, or you could paste it to the left of negative pi halves, and you'll see that the x-intercepts of the tan function occur at odd multiples of pi. So make careful note of this. The x-intercepts are at odd multiples of pi. And there's only one y-intercept for the whole tangent function, and that's at the origin. Okay, that's the only place where the tangent function hits the y-axis. Okay, and the same discussion goes with the cotangent function. The only exception is we choose this is the base period for the tangent function, because from 0 to pi, the cotangent function flows through its full range of values from negative infinity to positive infinity. So again, if we want a periodic graph, we just copy this blue branch right here, and we paste it at the beginning of this interval, and also as well as at the end of the interval. And so you can see we just cookie cutter it all down the x-axis. Okay, all along the x-axis, just pasting it to where the interval of periodicity ends or begins. Okay. So, and then, all right, so let's talk about the periodic extensions of the cosecant function and secant function. So that'll go something like this. Let me see if I can pull up a graph. Okay, let's see here. Whoops, sorry, wrong picture. All right, so here you see a periodic extension of the cosecant function. Now we know the cosecant function has period 2 pi. So the a graph of the cosecant function on one period, I'll accentuate in blue, so it would consist of this branch, okay, and then this branch. So that's one period of the cosecant function. And then all you have to do for a periodic plot would be to cookie cutter these two branches, copy these two branches, and then start pasting them at the end of this interval. So start pasting right here, these two branches, and you just keep pasting. Or you can start right here and paste it to the right of negative pi. And then the same discussion with the secant function. So the secant function, as you know, has a period of 2 pi, but the secant function flows through its full range of values on this interval, from negative pi halves to 3 pi over 2, and we actually call this the principal part. And we'll talk more about principal parts of functions later. But here is the piece that you'll cookie cutter. All right, so you take this cookie cutter piece and you start at negative pi halves and you start pasting it to the left, or you start at 3 pi over 2 and you start pasting it to the right. Okay, and then you'll have the periodic graph of the secant function. All right, so let's do some examples. Let's see, before I proceed, I see a note here. If we have a graph, or an equation that is, something like y is equal to a tangent of k x, like this, or y is equal to, say, a cotangent of kx. Just to keep in mind, we don't really talk about amplitudes of cotangent and tangent because they stretch to positive and negative infinity. But in a sense, a could be construed as an amplitude. But bear in mind, the periods though will be this. Okay, so you can do horizontal shrinking and stretching of these functions. So this is the period right here. You take pi and you divide it by k. And we know that k must be greater than 0. So if you have a negative, so for instance, if you have something like this, okay, you have to take the negative sign out of the argument. And the way you do that is that you know that the tangent function is an odd function. So by the odd property, you can move the negative sign out. And since the cotangent is an even function, you can just drop the negative sign in the argument. You'll have an equivalent function. All right, so next page, we'll do some graphing. I'll pull up the graphing calculator. Let's see, read the note here, see what we have to sketch. Okay. All right, so Okay, so we're there. Okay, so we'll configure our window properties to be Cartesian. We'll use radians, and we'll set our x-axis labels to multiples of pi, right? So like that. Okay, and so we'll look at the graph y equals tangent of x. Okay. Oops, the window properties didn't look like they got set right. Radians, please. There we go. All right, and so here's the graph of y equals tan x over several periods. Okay. Zoom in a bit. Okay. Now, suppose we want to graph the function y equals tan of 2x. All right, so let's attempt that. So we know from the previous screens that the period of the tangent function is pi. So in this case, we'll take the period to be, because we have a multiplier on x, the period would be pi halves. All right, so, okay. So we know that the, I guess you could say the period of the tangent function we usually take to be something like this. So here's how we can proceed with the sketch. It's a little bit tricky here, but the tangent function, its interval period ranges from negative pi halves. Oops, I shouldn't use. It's an open bracket, right? Because it's not defined at pi halves. So try it again. Tangent x is okay. So the tangent function is periodic on the open interval negative pi halves to pi halves. Okay. Now, for tangent of 2x, so the tangent function has a period of pi. All right, so that's the pi. So for the tangent of 2x, the period is pi halves. So basically what we'll have to do is we'll have to shrink the interval for which the periodicity happens, or the period happens. So the way we would deal with this is, since we're having the period, we would have the interval, the endpoints of the interval of the period. So for tangent function, let me go ahead and sketch the that should be x equals pi halves, I'm sorry. So next graph, x equals negative pi over 2, and then x equals pi over 2. So these would be the verticals for the tangent function. All right. Now, zoom in, zoom out. Okay, and just for clarity's sake, let's restrict the tangent graph to one period. Okay, so here the red curve is one period of the tangent function. So the way we would graph y equals tan 2x is we'll graph one branch on one period. Okay, and so now because we're shrinking the graph, we have to shrink the location. We have to adjust our vertical asymptotes so that they're now 1/2 the length of this periodic interval. So to do that, we would multiply negative pi halves by a half to get negative pi fourths, and then multiply pi halves by a half to get pi fourths, and that would constitute the endpoints of our interval of periodicity. All right, so let's do that. Okay, so now we will graph x equals negative pi over 4. That'll be the new interval, and then we'll graph x equals pi over 4. That'll be the new right vertical asymptote. Okay, so that means what we have to do is we have to redraw our tangent function in between the orange and the black vertical asymptotes. Okay, so basically just make it asymptotic and retain the original y-intercept. It passes through the origin. And so we should anticipate that the new function, y equals tan 2x, will be compressed, the red curve compressed between the orange and black vertical asymptotes. Okay, so, and I'll restrict it between 2 pi and pi. So negative pi over 2 is less than x, which is less than pi over 2. Okay, and that's shown in red. Okay, so let me take away this curve. Okay, and you can see we have a periodic graph of the tangent function, but one of the branches are asymptotic with, right here, negative pi fourths, and with x equals pi fourths. Okay, and you see here's the branch, and then all we do is we just copy this and paste to the right of this black line and to the left of the green line. Okay, all right. So now okay, so let's consider a shift of the tangent function. Okay. So let's work on the graph for y is equal to 2 times the tangent of x minus pi fourths. Well, as you might have guessed, this is simply the graph of the tangent function. No, I'm sorry, I've got that wrong. I meant to say y is equal to the tangent of 2 times. Sorry about that. Y is equal to the tangent of 2 times x minus pi fourths. All right, so this is essentially the curve we plotted before, y equals tangent of 2x, but we shift it to the right pi fourths units, okay? And so that'll change the location of our vertical asymptote. So let's go back and graph y is equal to tan of 2x, okay? And we note that our vertical asymptotes were x equals negative pi over 2, okay? Let's see, can I do 2? And then x equals pi over 2. That doesn't work, does it? I have to do one equation per line, okay? And then x equals pi over 2. Okay, so I'm sorry, it's asymptotic with pi over 4. Okay, so I need to change that to pi over 4. Let me recalculate the vertical asymptote. So that would be x equals negative pi over 4, and then x equals pi over 4. All right, so those are the vertical asymptotes. As you can see, this branch, this particular blue branch of the the tangent function is asymptotic with the orange and the black vertical asymptotes. And then we have the periodic extension. So you can see there's the tangent function. Now, all right, so now if we were to shift this to the right pi-fourths, well, when you do a shift of the function, the asymptotes will shift accordingly. So now the y-axis becomes an asymptote, and the line x equals pi halves will become an asymptote, right? So you can see the impact on the asymptote. So let's do that. Let's plot the graph y is equal to tangent of 2 times x minus pi fourths. Okay. So what is the effect? And that'll be shown in red. Okay, and let's zoom out, see the effects. Okay, so the red curve now should have an asymptote with the y-axis, which it does, and with the line, let's see, pi halves. So let's see. Okay, so the red curve. So just for emphasis, x equals to pi halves. That should be an asymptote for our, that's shown in blue. Okay, so there you see, as you can see, the red curve is asymptotic with pi halves right here, and with the y-axis right here. Where's the y-axis? The y-axis is right here. So this would be one period of the function y equals tan times 2 times x minus let's see, let me check that. We shift the curve pi fourths. Yeah, so instead of pi, the period is now pi halves, and the vertical asymptote has shifted from negative pi fourths to the y-axis, and also as well as from what is the other one? Yeah, pi fourths to pi halves. Okay, so the red curve is the what is that? That's the, let me check how we got this set up. The blue curve is y equals tan 2x, okay, and the tangent of 2x has vertical asymptotes. Okay, so let's analyze the shift here. This is the vertical asymptote for tan of 2x, and then when we shift it right, pi fourths, then this vertical asymptote gets shifted here, and then we know that, let's see, what else got shifted? We knew that pi fourths was a vertical asymptote right here for tan 2x, and then when we shift it right pi fourths, then pi halves, the vertical asymptote shifts here, and then the red branch is the shifted tan 2x function. Okay, so you can see that. All right, so the red branch is the shifted tan 2x function right here. So this is the shift. Okay, so we did so this graph is a combination of a horizontal shrink of the tangent function followed by a right shift. Okay. Okay. So how do we know? The next question, I guess, is how do we know the endpoints of the period of this function right here? How do we calculate the endpoints of this? All right. So here's how you deal with that. I'll write it here. Extend the page. So we know that for y equals tan x, okay, one period is between negative x equals negative pi halves and x equals pi halves. Okay, so for this function, y is equal to tangent of 2 times x minus pi fourths, we want to calculate the endpoints of one period. Okay, so that is found by setting 2 times x minus pi fourths equal to negative pi halves. This would be the start of a period, the interval of the periodicity, the interval of a period. And then we solve for x. So this would be x is equal to 0. Okay? And then the end of the period would be at x equals pi halves. So we set 2 times x minus pi fourths is equal to pi halves. And so when we solve for x, x equals to pi halves. So this would be the end of the period. And that was shown in the graph that we just walked through. All right. Now supposing, okay, let's consider, next page, the function, if we were to graph the function y is equal to, say, 2 times the cotangent of 3x minus 2. 3x minus, pi halves. All right, so we want to calculate the endpoints of one period. Okay, so the endpoints of one period are found as follows. Y equals cotangent x. Okay, completes one period. Between x equals 0 and x equals pi. Okay, so now what would be the completion of one period for this function, this modified cotangent function? So for the start of the period, for startup period, for y equals 2 cotangent of 3x minus pi halves. Okay, we set 3x minus pi halves equal to 0 and solve for x. So that means x equals pi 6 would be the start of the period. And then pi over 6, okay? And then for the end, okay, we set 3x minus pi halves equal to pi. And solve for x, and so we'll have x equals pi halves. All right, so that would be your preliminary sketch for this function would occur on the interval pi 6 to pi halves. Right. And I'll leave it to you to use the graphing calculator to complete the graph of this function. Check. Well, actually, I have it right here, so maybe I can just paste it. Let me give you a copy of it. So here would be the graph. Okay, right there. So identify pi 6, right? So here's pi 6 as a vertical asymptote, and then identify pi halves, right? So this would be the cotangent function shifted to the right, pi halves, or rather pi 6, right? It's shifted to the right, pi 6, because that would be the shift. And then the period is pi thirds, all right? So the period is pi thirds. Can we check that? Pi halves minus pi 6 is pi thirds. So the period is no longer pi, but it's now pi thirds. There's the shift, okay? And then we have the vertical asymptotes, and then of course it's a stretch, but the stretch is imperceptible for the cotangent function because it basically is already stretched to minus and plus infinity. But I think the literature does say that the amplitude would be this. So it does have an amplitude of 2. All right. So that's what I would expect you to be able to do this without the assist of, say, any technology. Be able to construct this graph. All right. It's comparatively very little calculation that needs to be done. It's just an awareness of the specific terminal point values and understanding of the graph of y equals cotangent x. All right, so let's go ahead and do some examples of the cosecant and secant functions. All right, so for the sake of time, I'll just go ahead and walk through the discussion of the graph, and let's see. Well, perhaps not. Maybe I'll explain it a little more detailed. Let's go back to our calculator, our graphing calculator. Where was it? Is this it? No. Was this it? No. What page? Here it is. Okay. So yeah, the cosecant function with translations and shifting, there's a special technique that can make it easy, and I'll show you how to deal with that. I don't think the book explains it too well. All right, so how about we consider the graph of y equals 1/2 cosecant 2x. Okay, actually it's quite simple. The way you would process this graph is you would start off by graphing the function y equals 1/2 sine of 2x. Okay, and then plot the cosecant function on top of the y equals sine 2x, because essentially 1/2 sine 2x is an asymptote or a guide for drawing the cosecant function. So that's the strategy. All you have to do. So clearly, this cosecant 2x function would have period of 2 pi over 2, which is equal to pi, and it would be shrunk by 1/2. The amplitude would be 1/2. Okay, so this is the period. So all we do is, so maybe I can do it manually here. So let's start off with the graph of y equals sine x. Okay, and let's do it. Let's just do perhaps one period. So one period of the sine function. So we'll go 0 less than or equal to x less than or equal to 2 pi. All right. So let's just we'll just do this, and then we'll cookie cutter it the rest of the way. All right, so there's one period of the sine. Let me zoom in, change the window back to pi. Change my x labels back to pi. One period of the sine function. Now, so to graph 1/2 of sine 2x, or we start off by graphing, we compress the sine function to a period of pi. So that means the way we deal with this is now our new period for the sine function is pi. So identify 0 to pi, and then we slice the interval, this green interval, into quarters. So let's see, pi. This would be pi halves. This would be pi fourths, 3 pi over 4, and then pi. All right, so we do that, and then so we know that this point is retained. We know that the sine of pi is still 0, but so since we're compressing, we know that the sine of pi halves is 1. But now, so 1/4, okay, 1/4 of through, use a different color, 1/4 through the interval on a period of sine x, okay, 1/4 through the interval on a period of sine x, the output is 1, okay? So that means when we compress it, 1/4 through the interval of sine 2x would have to have an output of 1 as well. So that means at pi fourths, which is 1/4 of the way through the interval 0 to pi, the output would have to be 1. Okay? Now, halfway through the interval of a period of sine x, the output is 0. So that means halfway through the interval of a period of sine 2x, the output would have to be 0 as well. Okay? So you have to retain that identity, so to speak. Now, 3/4 of the way, right here, through the interval, 3/4 of the way through the interval of one period of sine x, the output is -1. So that means that 3/4 of the way through the interval of one period of sine 2x, the output would have to be -1. Right? And at the end of the interval of sine 2 pi, excuse me, at the end of the interval of sine x, the output is 0. So at the end of the interval of sine 2x, the output should be 0. So here is the graph over one period of sine 2x, as shown in blue. Okay. Now, so what remains? Okay, so we have to compress this thing vertically by 1/2. So instead of an amplitude of 1, we'll have an amplitude of 1/2. So let me show that in, what's a good color? Perhaps black. Okay, so we just compress it by 1/2 vertically. Okay, so I guess, so multiply the outputs by 1/2 and we get this black curve. All right, so this black curve then defines the nature of our cosecant function. All right, so we would have the x-intercepts of the black curve would translate into vertical asymptotes. So we would have vertical asymptote at x equals 0, a vertical asymptote at pi halves, and a vertical asymptote at pi. All right, so for one period of 1/2 cosecant 2x. So you see how you start off with the sine function, you change cosecant to sine, graph that, use that as the reference for the graphing the cosecant function. And so now we're ready to graph the cosecant function. So we come here to this local maximum for the 1/2 sine 2x, and then we just draw the branches in yellow like this. So it will be drawn like this. Okay. And then you use the cookie cutter approach and just copy, paste, paste. Okay, so we can validate that perhaps by seeing if the yellow curve matches up with what the computer will say. So we want y is equal to 0.5 times the cosecant of 2x, and we want to just look at it on one period. That's the period is pi, I'm sorry. Okay. And so they do match up. So the computer drew it in blue, a light baby blue. Oh, this branch I made an error, didn't I? I didn't make it touch the black curve. Ah, good catch. So let me erase this branch. Yeah, the computer's right. I should have drawn my yellow branch. I should have used the black curve as the guide, and I used the blue curve. Okay, so be careful not to get them mixed up. All right, so you see how we sketched the this complicated function 1/2 cosecant 2x without the use of any calculators. It was pretty straightforward. So if you have knowledge of the graph of the sine function, you can pretty much graph just about anything. Okay. All right. So now that leaves us with the task of having to graph the shift of a cosecant function or a secant function. So let's process that now. So let me erase this. Okay, so let's close these out. And so let's consider graphing. Let me turn those off. How about y is equal to 1/2 cosecant of 2x plus pi halves. All right, now we know. Okay, so here's how we can identify the a period, one period for which we can sketch the graph of. So let me write a couple of notes here at the bottom. Let me erase this. Erase all of this whiteboard stuff. Since y equals to cosecant x completes one period between x equals 0 and x equals 2 pi, okay, the function y equals 1/2 cosecant of 2x plus pi halves completes one period as 2x plus pi halves varies from 0 to 2 pi. Okay. So the start of the period for this function would be found by setting 2x plus pi halves equals to 0 and solving for x. So that means that x would equal to negative pi fourths. And then the end of the period would be found by setting 2x plus pi halves equals to 2 pi, solving for x. And so at the end of the period would be x equals 3 pi over 4. All right. So now let's go back and work on the graph over one period at least. Okay, so let's get rid of this. So we're graphing y equals 1/2 of cosecant of 2x plus pi halves. So now, the period starts at negative pi fourth. Okay, so that would denote a vertical asymptote at x equals negative pi fourth. So let me sketch that. So x equals to negative pi fourths, because we know at the endpoints of the period of the cosecant function are vertical asymptotes. And then the period ends at x equals 3 pi over 4. Okay, so the green and purple lines are my range of a period of the function. Okay, so the graph has to be sketched. Now, so between negative pi fourths and 3 pi over 4, we have to split the interval into four equal sublengths. Okay, so the midpoint would be pi halves. All right, so that would be, let's see, where would the midpoint be? It's hard to see. 1, 2, roughly right here, huh? 1, 2. Let's see, 1, 2, 3, 4. So it would be here. This would be the midpoint. So let me 1, 2, midpoint here. So, and then we divide, let's see, wait a second. The midpoint of the interval from negative pi fourths to 3 pi over 4. So that would be not that, but something else, right? You to find the midpoint, you add the two together, which would be 2 pi over 4, and then you have it. So it would be pi fourths, I beg your pardon. So it would be pi fourths would be the midpoint of this interval. So mark pi fourths as the midpoint of the interval between negative pi fourths and 3 pi over 4, and then split. Let's see, 1, 2, 3. Do I still have it? I still don't have that right, do I? Let's see. This would be pi fourths, pi halves, 3 pi over 4, 4 pi over 4. Let me check. It looks a little bit off, doesn't it? So 2 pi over 4, pi over 4. Let's see, so we have 1, 2, 3, 4, 5. Oh. What is the midpoint of this interval? So we have to use the midpoint formula, right? So the midpoint formula says to find the distance. So that would be 4 pi halves, right? It would have to be pi halves. Let's check pi halves. I think it would be pi halves, right? Let's check. Sorry, I have to find the midpoint of the interval. Okay, so the midpoint of the interval. So it would be pi halves away starting at negative pi fourths. I see now. Okay. So let's go back here. And so we would start here, and then we would go pi halves. So this would be pi fourths. So it would be roughly, let's see, the interval here would be pi halves plus pi eighths, pi halves plus pi eighths. So that would be 3 pi over 8, I believe, would be the midpoint. Let me check. 1 second. Let's see, this is 3 pi over 4, right? Okay, so 3 pi over 4. Pi halves. Yeah, it would be pi fourths. Pi fourths would be the midpoint of the interval. Yeah, I'm sorry, pi fourths. I was kind of thrown. Yeah, so you add the 2. When you add the 2, you get 2 pi over 4. And then you take 1/2. Yeah, so you have to use the midpoint formula. Yeah, so 1/2 of 2 pi over 4 is pi fourths. Sorry about that. I just needed to check. Convince myself that pi fourths is the midpoint of the interval. So right there is the midpoint. And so we're going to sketch a sine function on the interval from negative pi fourths to 3 pi over 4 between the green and purple lines. So at the halfway point, at the midpoint, we know that the sine function on this compressed interval will be 0. And let's see, right here, at the y-axis, what would that result in? Let me think about that. Pi fourths. Okay, so this is what? Pi fourths. This is negative pi fourths. So the midpoint is 0. So the midpoint of the first half interval of the period of the sine function, the output is 1. So our sine function would be that. And then the midpoint of the second half of the interval, at this midpoint, right here, then the output of the sine function is negative 1. Okay, so if this is pi fourths, this is 3 pi over 4, so this would be pi halves right here. So this is pi halves. And so our guide, and then, okay, so and then we would have to have it because, well, this would be sine of, all right, let me sketch it. Let me finish the sketch. So what I'm drawing right here, the blue curve, is y is equal to sine of 2x plus pi halves. All right? It's basically sine of 2x with period pi, shift it to the right pi fourth units. Okay? Now, okay, so now the only thing that remains to be done is to compress this sine wave by the amplitude factor of 1/2. All right, so we'll do that in black. Okay, so now we have that. And then, so we use the black curve as our guide for completing the sketch of the function y equals 1/2 cosecant 2x plus pi halves over 1 period. So, oops, I got to draw my vertical asymptote. There's one more vertical asymptote at the x-intercept, so we've got this. All right, and so we'll draw this in green using the black curve as a guide. So asymptotic there, and then asymptotic there. So like that, like so. And I believe that would be the answer. Yes. Okay, for 1 period. So to sketch over multiple periods, you just copy the green curve and you start pasting it to the right of the purple curve, or you paste it before or to the left of the green curve for periodicity. So it may be the case that I'll ask you to sketch 3 periods of this graph. So be able to make sure that the local minimums are correct over 3 periods, and as well as the local maximums are correct over 3 periods, as well as the vertical asymptotes are correct over 3 periods. Okay. So I encourage you to practice this. I can't cover all 6 functions and the variance of their shifting and stretching and whatnot, and period calculations and so forth. So WebAssign will do a pretty good job if you go through the WebAssign homework problems and do a number of examples. And so I'm hoping that you go through all the different combinations and understand how to graph these functions. That's all I want to do with this for now. Checking if there are any other things. What I want to do now is I want to move on to the next topic, I think this is the last topic of Chapter 2, and this would be applications of all this stuff that we've been doing in Chapter 2. And it's so the next topic will be called harmonic motion. Okay, so I want to talk about harmonic motion. I believe this will be the last topic of Chapter 2, some applications. All right, so what do we mean by harmonic motion? I can show you a right now. What it's a concept from physics. It's like when you take a weight and you dangle it from the end of a spring, and the spring is, say, attached to the ceiling, and you pull on the spring with the weight, and then the weight bobs up and down. Okay, and so that bobbing motion is called harmonic motion, and it looks something like this. Let me stand by while I paste a picture into whiteboard. Okay, so harmonic motion. Here's an example. So look at the graph of y equals sine of t. And compare the math graph, okay, with the vibration. Okay, so this red thing is where the spring is attached to a fixed platform. And here we have a weight at the end of the spring, and you tug on the weight, and you see that the weight bobs up and down as the spring compresses, the weight goes up, the spring stretches, the weight goes down. Okay, and so you have this, for an ideal spring, you have this up and down motion. And if you go to the center of gravity of the weight and you plot its position with time, you notice that it'll trace out almost y equals sine of t. So this is what we mean by harmonic motion. And this is the case of an ideal spring. Of course, in reality, the spring will eventually stop compressing and expanding, and the harmonic motion will die out and the weight comes to a rest. That's called damped harmonic motion, and we'll talk about that in Chapter 7. But this is idealized harmonic motion, where the spring never loses energy. It expands and contracts uniformly for all of time. Okay, so we have what's called simple harmonic motion. So let me paste a definition into whiteboard. And it should come as no surprise to you as to what the definitions I'm about to present are. So simple harmonic motion. So if we have an equation describing the displacement y of an object at time t. Okay, it's your standard sine function. We call it sine omega t or cosine omega t. Either function can describe harmonic motion. And so we have these definitions. The amplitude, as usual, is the absolute value of the coefficient on the trig function. The period is, as usual, 2 pi over omega. This cursive w is called omega. It's a Greek letter omega. And then, okay, so now we have the notion of a new concept called frequency, which is 1 over the period. It's the reciprocal. Okay, so the reciprocal of period is called frequency. And what frequency is, let me show you from the preceding slide. What frequency is, say right here. Right here we call it 1 hour. Okay, so it takes maybe 1 second. That's too long. So that's very slow motion, right? Make it 1 second. 1 second. And so in 1 second, we have the completion of 1 cycle of the harmonic motion before it starts repeating itself again. Now, suppose in this 1 second, I had the completion of a number of cycles like this, say maybe 5 or 6 cycles. So that means in 1 second, I complete 6 cycles, so my frequency would be 6. Okay, 6 cycles per second. And cycles per second are often written as hertz, Hz, hertz. Okay, and then the period, of course, would be 1/6 seconds. Okay, so the reciprocal of seconds is hertz. So we have these ideas. So let me show you an example from physics. Bear with me while I paste another example into the whiteboard. Let me start a new page. Okay, so the frequencies, okay, so these functions, y equals a sine 2 v. That's a Greek letter. I forgot what it was called. Eta. Okay, we'll just call them v for now. These functions have frequency v because the period, okay, so the period is 2 pi v over 2 pi, which is equal to v, okay? And so we said that the number of cycles per unit time is frequency. So to calculate the frequency of this curve, of these two functions, you just take 2 pi, you take the multiplier on t, which is omega. In the previous slide, I think we called this omega. So this right here is your omega. Okay? And so omega over 2 pi, and in this case is equal to nu, I think it's called. Well, not nu, I forgot what it was called. I forgot what that letter was called. I'll have to look that up. Somebody will have to tell me. So this is your frequency. All right, so a vibrating string example. The displacement of a mass suspended by a spring is modeled by this function right here, where y is measured in inches and t is in seconds. So we want to find the amplitude, period, and frequency of motion of the mass. Amplitude, period, and frequency of the motion. All right. So the amplitude is simply the absolute value of the coefficient, which is 10 inches. And then the period would just be 2 pi over omega. And so in this case, omega is the multiplier on t. So the multiplier on t is 4 pi, so the period is 1/2 second. Okay. And let's see, the frequency, of course, is just the reciprocal of the period. So that would be, what, omega over 2 pi. And so omega being 4 pi, so the frequency is 2 hertz. And then, of course, we use our techniques that we've been talking about ad nauseum to sketch the graph of the periodic motion right here. So it's a sine wave with period 1/2, as you can see. It goes through the sine function traverses through its full range of output values from 0 to 1/2. It ranges from -1 to 1. It's stretched by 10, so this is 10, obviously. And this is -10 right there. And the frequency is 2 hertz. Okay, so in 1 second, right here, here's 1 second, we complete 2 cycles. You can see that in 1 second we complete 2 cycles. So it's kind of a low frequency motion. I think the human ear, I don't know what frequencies the human ear can hear sound from, but I think there may be an example forthcoming. All right. So some more examples. Vibrations of a musical note. So let's do another problem. An interesting problem from physics. All right, so let me copy it. Bear with me while I copy it. So in this example, multi-part question, and this could be in WebAssign as well, we have the following. A tuba player, good. Okay, a tuba player plays the note E and sustains this sound for some time. For a pure E, the variation in pressure from normal air pressure is given by this. Okay, so where V is measured in pounds per square inch. So V is essentially pressure. So the air pressure that this guy has to exert to get the note out is this formula in terms of T. So we want to find the amplitude, period, and frequency of the pressure with time. Okay, so the amplitude, of course, is 0.2. The amplitude is simply the coefficient on the function right there. So there's your amplitude, circled in red. The period, okay, so we take, to find the period, we just take the argument on t, and we go 2 pi divided by 80 pi. And so that's equal to 1/40th seconds. So that means 1/40th of a second. And then the frequency is 40 seconds. 40 hertz, excuse me. Okay, so that means this sine wave, okay, goes through 40 cycles in a second. So that's pretty significant. So that's something you can definitely hear. And so what is part B? Okay, so we want to sketch the graph. So let me pull up a picture of the graph. I'll give it to you, because this would, by doing this by hand, would be pretty challenging, because you have to show you'll have to show 40 cycles, 40 periods in a 40 periods in a second. Okay, so and I think in the graph solution they just show 20 periods over a half a second. So let me pull that for you. So here's the sketch over a half a period at least. Over half a second, that is. Okay, so over half a second you'll have 20 periods. Okay, 20 periods, and then you can see it ranges from -0.2 to 0.2. So there's the graph. And then the next question is, all right, so let me move this out of the way so you can see it. If the player increases the loudness of the note, how does the duration for V change? Well, if the player increases the loudness, then the amplitude increases. So you would have to replace the amplitude by a larger number for loudness. And if the note goes flat, okay, if the player is playing the note incorrectly and is a little flat, how does the equation for V change? Okay, and so the frequency is decreased. So if you decrease the frequency, that causes the flatness of the tone, right? And so the frequency, remember that the frequency is 80 pi over 2 pi. So to decrease the frequency, let me write this out for you. Frequency F is 80 pi over 2 pi. So decreasing the frequency, you have to decrease the numerator to achieve the result. So that the equation would be altered by making this 80 a smaller number, say 70 or 60, and that would cause it to go flat. All right. Okay, and so one more example, another physics example. Let's do that. Let me see the extent of this problem here. Okay, let me bear with me while I paste it in to whiteboard. Okay, so modeling the vibration of a string. One second, I need to configure the page so that it looks correct. All right, so let me copy this. Copy, new, don't save, paste. Let me select this. Okay. Okay, so here we go, right here. Okay, so here we have a problem where a mass is suspended from a spring, and the spring is compressed a distance of 4 centimeters and then released. So as shown in this figure, you compress the spring 4 centimeters and release it. It's observed that the mass returns to the compressed position after 1/3 seconds. So we want to find a function that models the spring of the mass. Okay. All right, so the motion of the mass, so here's how we deal with it. All right, so whenever you have a spring, you're going to have, with motion, you're going to have harmonic motion. So the motion of the mass is given by a harmonic equation. Harmonic function, harmonic equation. I have to be careful what I say about that because there are different kinds of harmonic equations. So we'll say a harmonic equation of motion. Okay, so the amplitude is 4 centimeters. You can't go higher than 4 centimeters or lower than 4 centimeters because that's all the energy that you put into the system. All right, so it can never exceed 4 centimeters in either direction with respect to this reference line right here. This is called our reference line. So it'll never go above 4 centimeters nor below 4 centimeters. So the amplitude is reached at t equals 0. So we have, if we have position and time, okay, this is what our graph will consist of. Position is no, actually it's the other way around, right? Position is a function of time. Sorry, I have those backwards. We have time versus position. That's what we're plotting, okay? So we're plotting time and position, these ordered pairs. So our abscissa is time and our coordinate is position. So that means at time t equals 0, we have a position of 4 centimeters. So we know that at t equals 0, the sine function output is 0. Okay, so the only other choice for harmonic motion then, we would need the services of a cosine function, because at t equals 0, the cosine function is 1. And so if we multiply 1 by 4, we'll achieve the desired output. All right, so we have to have something like this. Now, so the period, we said the period was 1/3 of a second. So that means it goes through its full range of displacement after 1/3 of a second. So the period, we know for a cosine function, or for any trig function, or for cosine, sine, cosecant, and secant, that is, the period would equal to 2 pi divided by the multiplier on t, which is omega. And in this case, the period we said was a third. So solving for omega, omega then is equal to 6 pi. So the equation of motion then is y is equal to 4 times the cosine of 6 pi t. Okay, so now how do we sketch the graph? Okay. Okay, so we need to sketch the graph. And let's see if we can do it without the assist of a computer. So we know we need to sketch y equals 4 cosine t, and the period is a third. So that means if we have our position, so we'll call it this y, and then we'll have our t-axis. The period is a third, so we'll have 1/12, 2/12, 3/12, 4/12. So here is 1/3. And we know the cosine function ranges at t equals 0, we'll have 4. And then 1/4 of the way through a complete period, the cosine function will attain a value of 0 at 1/12. And then halfway through the period, the cosine function attains its minimal value, so that would be -4. And then 3/4 of the way through the period, the cosine function attains a 0. And then at the end of the interval, at the end of a period, the cosine function, no matter how it's transformed, will attain its maximal. So this would be the graph of the displacement of the pendulum with respect to time. All right, so one more summary slide, and I think we've got a few more. Okay, I see. A couple more examples from engineering. Okay, so let me give you a summary about harmonic motion in general. So I'm going to paste another slide. Let me see here. So our general takeaway with respect to harmonic motion, let's summarize this. Okay, so in general, the sine or cosine functions representing harmonic motion may be shifted horizontally or vertically. So here you have a horizontal shift right, and followed by a vertical shift up, okay? Or you could shift it right. Okay, so they're using sine or cosine. So you can have things like this. And so the vertical shift indicates that the variation occurs around an average value b, all right? So in other words, what this means is that this would be the average position of the weight, okay? And it would be d, okay? And if we were to use the sine or the cosine function. And then the horizontal shift indicates the position of the object at t equals 0. So at t equals 0, the object, it just depends on your reference frame, your physical reference frame. You could have the object shifted away from what you consider from the camera, for instance. If the camera is located at the origin and you're photographing the position with time, so it's the same thing that we've been talking about, okay, and so on. So not much there really, other than stuff we already know. Okay, so let's see. How about an application of this particular slide? Interesting problem. So modeling the brightness of a variable star. So that's an interesting problem. We'll do something from astronomy. Okay, not that there's much application for astronomy here in Alaska because of the persistent cloud cover, but anyway, we can try. So let me make sure I have the complete problem. All right. So in this problem, a variable star is one whose brightness alternately increases and decreases. So for the variable star delta phi, whatever, the time between periods of maximum brightness is 5.4 days. And so the average brightness or magnitude of the star is 4, and its brightness varies by plus or minus 0.35. So we want to find a function that models the brightness of the star as a function of time, right? So in this case, we'll use the generalized cosinusoidal function, right? So we want to, for this case, the key is, so we have brightness varying, so this would be the magnitude would be your coefficient on your cosinusoidal function. And let's see what else we would have here. So the average of the output is 4, okay? And so that would force us to have to use a B value from the previous slide. And let's see what else we would have here. I don't think we would have to worry about a C value. Okay, so, but anyway, we would resort to using the generalized equation of harmonic motion where the initial output is not 0. So if you're using harmonic motion and the output at t equals 0 is not 0, then you use the cosine function. If the output at 0 is 0, then you probably want to resort to using the sine function. So here's the generalized equation for harmonic motion. Okay, and in this case, the amplitude is maximum. The amplitude is a maximum variation from the average brightness. Okay, so the amplitude, let me write this down. Amplitude is maximum variation from average brightness. Average brightness. Okay, so the average brightness, okay, is 4. And so the variation from 4, we go 0.35 in this direction, and then we go 0.35 in the next direction, the other direction. So this is the brightness is confined to this band, okay, between 3.65 and 4.35. So your amplitude is readily discerned to be 0.35, and B is 4. Okay, so we got that so far. Now we're given a period of 5.4 days for the variation of the brightness. So now there's no reason to use C because we can consider, since we're looking at the object straight on, okay, there's no reason for an offset for C. I can't think of an explanation of why we would want to use C. So that means we can simplify now. Our equation becomes y is equal to 0.35 times cosine of omega t plus 4. So all we need to do is calculate what omega is. All right, so the period is 5.4 days. Okay, and so omega then is just 2 pi over your period. So that would be 2 pi over 5.4 days, which is equal to 1.164. All right. Okay, and so why is there no horizontal shift? So let me write down why there's no horizontal shift. Okay. If we take t equals 0 to be the time when the star is at its maximum brightness, then there is no horizontal shift. Now, if this were not the case, then you would have to compute a C value based on the other parameters that we just derived. And that would involve having to solve for C, and you'd have to take the inverse of the trig function, and we haven't done that yet. So for now, just take t equals 0 to be either the maximum or minimum output, depending on your choice of cosine or sine. So if it's cosine, if you're using cosine form of harmonic motion, take t equals 0 to be the maximal output. And if you do that, you won't have to worry about the C value. So now you just wire it up. So y is equal to 0.35 times the cosine of 1.164t plus 4, excuse me, 4. Okay, so there's your, and of course we don't have C. If we were to inject a C in here, then the maximal output at t equals 0 would not be 4, and we would have issues. Okay, or the maximal output at t equals 0 would not be 4.35. So we would have issues with that, and it would be much harder problem. Okay, and so to sketch the graph, well, I'll let you go through the details of understanding the sketch of the graph, but I'll paste it in here just for good measure, just for completeness sake. So it's just a cosine function with a modified amplitude and period shifted up. So here it is. So the average value output is 4. The maximal occurs at t equals 0, and the period is 5.4, as stipulated in the problem. Okay. Let's see here. All right. So something that is of interest to folks in Alaska, and that would be modeling the number of hours of daylight in a day. Okay, so let's do that next as an application. So let me see if I can. So in Philadelphia, at 40 degrees north latitude, the longest day of the year is 14 hours, 15 minutes of daylight. And the shortest day has 9 hours and 10 minutes. So we want to find a function L that models the length of daylight as a function of t. And t is, of course, the number of days from January 1st. All right, so let's do that first. All right, so we want to model, find a function. So now, the minimum, okay, so the minimum daylight is at 9 hours and 10 minutes. So an ideal function is if we start with the day, if we start on the day with the minimum daylight hours, we can use a sinusoidal function. So for part A, we're going to use a function that looks something like this, the generalized harmonic function for a sine wave. So this would be y is equal to A times the sine of omega of t minus c plus b. So we're going to use this equation because we're going to start off with hopefully the minimal value of the output. So what do we have here? So we need to find what A is. So A is the distance from the average value of the function to the peak value of the function. Okay. Oh, so do I need to give you? I need to give you a chart. All right. So I need to give you some data. So let me pull up a data sheet for you, showing how daylight varies, how the hours of daylight vary at varying degrees of latitude. All right, so let's use this. So remember, A is the average value of the output. Okay, so using this chart, we can see the maximal and minimal hours of daylight for a given month, during a given month at a given latitude. So Philly is at 40 degrees latitude, so we'll be using the blue curve. Okay, and so the maximum, so it's kind of hard to read the curve because I think it got kind of smeared when I scanned it. So A is the average value of the blue curve. And so the average value of the blue curve would be A is equal to 1/2 the maximal value. And the maximal value is 14, okay, right here. So say 14, and the book estimated at 5/6. Okay, and that's what the problem says, right? So the problem stated the maximal number of daylight hours. Let's check. 14 hours and 50 minutes. So 50 minutes is 5/6 of an hour. And then the minimal value, so that would be below the average value. So the minimal, so to calculate A, you take the maximal value, and then you subtract the minimal value, which is 9 hours and 10 minutes, which is 1/6. Okay, so that's how you find, because the because somewhere right here at 12, I think, yeah, at 12, this is your reference line, and so you want to take this distance, okay, and then you want to take this distance right here, and you want to find the average of these two distances. And well, this distance is positive, and this distance is negative with respect to the average line. And so when you do the calculations, the amplitude will be 2.83 hours. Okay, so that's the variation. All right, so what is the period? Well, omega, since there are 365 days in a year, the period of this model would be 2 pi over 365, so, because So that's approximately 0.0172. And so this is the period because we expect that the daylight hours on each day of the year is different. But at the end of the year, the daylight hours start repeating themselves for the rollover into the second year. Okay, so the repetition of the outputs of the daylight hours occurs on an annual basis. So like on March 1st of one year, the number of daylight hours will be the same as March 1st on the second year. Of course, this is an estimate. We're not taking into account leap year and all that other stuff. Or maybe we are. Who knows? Perhaps we. Okay. Anyway, so the average length of daylight is 12 hours, as I showed you in this black reference line. So the average length of daylight is equal to 12 hours. And so what this means is that we shift graph up 12. Okay, so B is equal to 12. Okay, so where does the graph, the blue graph, attain its, where on the graph does the daylight hours equal to 12, okay? And so that appears to happen, does it say in the problem? It doesn't say. So we can kind of estimate where the blue graph attains its average value of 12 hours, say, right here. Let me see. Did I give you all of the information for this problem? Okay. So say about 2/3 of the way through March, we have a situation where the number of daylight hours equals to the average length of the day. So let's say for the sake of brevity, on March 21st, daylight hours equal to 12. Which is basically the start of spring, right? And so this occurs on the 80th day of the year. Okay, so I'll give that to you. So this occurs okay, because let's see, January has 31, February has 28, so that would be 59, and then 59 and 12 would be 80, right? So this occurs on day 80. Okay, so you see how that works? So that's why I chose March 21st, because 80 is a nice number to work with. It's a multiple of 10. Okay. All right. So this means that the average value occurs. So that this would be our C value. So C, where the average value of the function occurs, would the time, okay, excuse me, the number of days since January 1st where the average value of the function occurs would make C equal to 80. Okay, so that would define our C value. Okay, so, all right, and so we have all the information now. So let's see here. So we have Y is equal to the amplitude, which we said was 2.83. This is a hard problem. And then times sine. And let's see, our omega. Let's see, did we calculate omega? Yeah, 0.0172. Times time. The average value occurs at day 80. And then we add our 12 because that's our average value. All right, so is that all I want to do? Okay. All right, so let's skip part B because so part B is a little bit complicated and rather involved solution. So I'm gonna skip on that problem because we have to move on. All right, so let's do one problem from electrical engineering. And this will be the last problem of the chapter that we'll discuss. So I'll walk through this. This is actually from electrical engineering. So another situation where simple harmonic motion occurs is in alternating current for generators, AC generators. So alternating current is produced when an armature rotates about its axis in a magnetic field. So kind of hard to see here, but I'll accentuate the armature in green. So you've got this coil, okay, that's rotating in a magnetic field. Okay, so you hitch it up to a shaft and it rotates. And so when it rotates from the wire, you get alternating current. So this is basically a simplified schematic of a generator. And so we have voltage as a function of time. And of course, E sub naught is the maximum voltage, and it depends on the strength of the magnetic field. And let's see here, what else? And omega over 2 pi is the revolutions, the number of revolutions per second of the armature. So omega over 2 pi is the frequency. All right, so in this problem, we have 110-volt household current, alternating current varies from 155 to minus 155 volts with a frequency of 60 hertz cycles per second. So we want to find an equation that describes the variation in the voltage. Okay, and here I have it worked out. So the variation in voltage is simple harmonic, frequency 60, so that means that omega over 2 pi is equal to 60, so omega is equal to 120 pi. And at t equals 0, the voltage is 155. So using the equation, we have to use the cosinusoidal function because we have a non-zero output at t equals 0. So E of t is equal to a cosine omega t, which is equal to 155 cosine times 120 pi t. So that if you hooked up an oscilloscope to your socket in your house, which I would not recommend, you would see a graph of this function on an oscilloscope if you have proper electrical provisioning in your residence. All right, so that is chapter 2. So what do we have going on here? So we'll have our test on chapter 2, and so you'll need to look in WebAssign to see if it's there. If this is a class where I said I was going to give a paper-based Chapter 2 test, so make sure you listen for announcements. I may or may not give a paper-based test for Chapter 2. And of course, you have your WebAssign assignments for Chapter 2, which you must complete. And as always, do not spend inordinate amounts of time trying to figure out the solution to one problem. If it takes you, say, longer than 10 minutes to get a solution to one problem, send me an email and I can post a hint or another video. But at the same time, please do not delay doing your WebAssign assignments. Please start as soon as possible. Okay, so that's it for Chapter 2. On to Chapter 3.